So let's get started. Today we're going to talk about transfer functions and block diagrams in details. More specifically, I want to equip you guys with the tools to analyze practical, complex control systems. You may be very familiar with something like this. I have a plant that I want to control, let's say P, and then I have a controller. This is the most basic block diagram for a control system, feedback system. And you can write out, you can analyze the input-output relationship from here to here very easily. But in practice, this is rarely the actual control scheme that is implemented. In practice, there are always different elements in the controller that will go into it. So an example is as follows. In practice, you can have something like this. So what if in practice you're given actually this type of block diagram and you want to still easily be able to tell what is the relationship between the input and output? It is not that trivial anymore. So today's goal is to somehow give you a concept and tools to go from here to here to let you be able to lump this entire thing up and obtain an equivalent transfer function, a single closed-loop feedback transfer function. Then you can apply a lot of analysis. So that's the goal. And we'll focus on linear systems, and we'll focus exclusively on transfer function logic. So we won't do frequency response, etc. Everything here, if I don't put any notations, these are all transfer functions. These are all in the Laplace domain transfer functions. So that's the setup. And let's start from the basics. So transfer function logic. The simplest one is this. If we have an input-output passing through a transfer function in a block diagram, G, then the output is written this way. So input kicks in, connects with the output by this transfer function g of s. And then if you have more elements into it, so let's suppose your input is more complex. Then we have the summing junction. This is called a summing junction. And then different signals go into the summing junction. We will use the notation plus or minus to indicate the signs of these signals going into the summing junction. So what I mean by writing it this way is that this signal, let's call this R tilde, is Rs plus whatever that goes into the summing junction. And if there's a minus sign in any of these, it's going to become minus. So pretty basic. And then we have a pickoff point. So it is common that a signal is being used by many channels. So when we write it this way, a signal goes into here. There's no summing junction written, but it's just a node that connects to different branches. Then all the signals are the same going through these different branches. So this C1s equals C of S, and this C2s equals C of S as well. So this is a pickoff point. Question?
So again, whenever an arrow is going into a summing junction, it's going to be plus, and whenever it's leaving that summing junction, it's minus?
So the summing junction, is a good question. So summing junction can be written this way. The signs near the end of the summing junction, near the end of these arrows indicate the signs of these signals.
Oh, it's just, okay.
Yes, if it is minus, then you write a minus. So the way that I use the notation here is it can be either plus or minus, and depending on whether it's plus or minus, the signs here will change. Okay, so that's the basic elements. Summing junction, pick-off points. In here, we have summing junction like this. This is a pick-off point. So that means the signal going into here is exactly the same as the signal on this top branch. Okay. In some textbooks, they use summing junctions like this. They put a cross sign inside, but often for simplicity, we just write a circle. So this is, if we just have one transfer function in here, we can easily stack transfer functions in series and in parallel. So we can say a signal will pass through two steps of transfer functions and get an output. It is basically this picture applied twice iteratively. So you can see that this signal here is going to be G1 S RS, all right? So this is just applying this logic. Output equals input multiplied with the transfer function. And then this signal goes through a second stage and gives you the output CS. So it's going to be G2 S G1 S RS. So this is two transfer functions in series. And I recommend you to always write it this way. So input on the right-hand side, put it at the end, and then the second to the last item is the transfer function. So think of it this way. This signal hits G1 and then hits G2. So in this series, write it this way, okay? This matters not much in linear systems with single input, single output. But if you step into multi-variable systems, this is extremely important. You follow this convention. So that is in series connection. You can also do in parallel connection. So a signal goes through a pick-off point, passes through three channels of transfer functions. Let's call still R, and then generates an output. The output is a summation of the three channel outputs. And then in this case, it would be, so you can do it from this foundational input-output relationship. So this signal passed through G1, then the output here will be G1 times R. So that's a signal here. And then the signal here will be G2 R. And then same thing, this is G3 R. And then you have a summing junction. So if I say summing junction is plus, 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 then add these three together. So it's going to be G1 R, G2 R, G3 R. You can combine things. So they all have the same R. So you can write it as G1 plus G2 plus G3 R. So that's in parallel construction. For simplicity, I have omitted the S in some of these block diagrams. So that's in series, in parallel. Let me open the door actually. It's a little bit warm. Okay, so these are the basic block diagram components. Now let's talk about this one. In feedback form, how the transfer function will look like. We can use these elements to analyze the signal relationships. So let's say this is U over here, and then we have a summing junction. Let's say this is plus. The summing junction coming from the other end of the summing junction is Y signal, so this is Y, and then this is minus. So the signal over here is going to be U minus Y, and then this signal passed through the transfer function. The first transfer function is C. So that means the output over here will become C. I'm going to write it this way. So this is C times U minus Y. And then this signal passed through the second transfer function P. So that means the signal over here, it equals to P C U minus Y. So as a rule of thumb, when we write the quantities in Laplace domain, we use capitalized letter. So I'm using capital Y over here. So we know that this signal here is equal to PCU minus Y, and then it also equals, because this is a pick-off point. So these two signals must be the same, and then therefore you have a relationship. So that means, write it this way, Y it equals to PCUY. And then you can combine terms a little bit. So I have a Y on the left-hand side, I have a Y on the right-hand side. So that means putting all the terms about Y to the left-hand side, I'm going to have, this is PC negative Y, moving to the left becomes PCY in positive sign. Then on the right-hand side, it becomes PCU of S. Okay, so we're almost there. Now you can see I can, this immediately gives us this. Combine the two terms about Y on the left-hand side. I'm going to have 1 plus PCY left-hand side equals PCU on the right-hand side. So remember, what are our goals? Our goals, when we write it this way, is we want to understand, after all these signal flows, what is the relationship between my input and output? So now we have it. So this equivalently gives us this, Y equals PC over 1 plus PC times U. So this is the transfer function between the input and output in this feedback loop. So I did it with a negative sign in my block diagram. You should be able to obtain the result if this is plus. What is the relationship? What is the overall transfer function? So do it as an exercise. Okay, so we went through this math over here. I'll tell you a trick right now. It turns out experienced control system engineers, by looking at this, they don't need to go through all the steps over here. They can immediately tell what is the input-output relationship. So this formula has a way to remember very easily. So the way to remember this result over here is as follows. Look at the signal. Look at the flow of the signal. My input U goes through two passes. The first pass is this pass, is this direct pass, feed-forward pass to the output. And then some part of it, as the signal goes through here, it enters this feedback loop. So the way to look at that formula is that you can see in the numerator is P times C. That's exactly the transfer functions in the direct pass. So you can see P times C is directly the numerator. So put that in the numerator of the transfer function. And then whenever you have feedback, you are going to have a denominator. So the feedback, if it's negative feedback, the denominator will be 1 plus the overall, so from here. So for the second pass of this input, it goes through here, here. So it's 1 plus P times C, which is all the transfer functions in this feedback loop multiplied together. So that's how you can remember this formula very easily. Numerator, direct pass. Denominator, if it's negative feedback, is 1 plus whatever, all the transfer functions in this loop. Okay, so take that back and do some exercises. When you analyze this formula again, work on, so as an exercise, work on two things. First is the case when it's positive feedback. First, work on that scenario. Change to a positive, change to a plus sign. Second, work on this. Second, work on this scenario where I have another block in this feedback pass. Work on the transfer function. You can use the analysis mathematically or think about the formula that I just discussed. Okay? So it turns out this one can be written very quickly as well. The output relationship would be, you should be able to arrive at this result in the end. And then this formula is very easy. If you comprehend what we discussed about the reasoning behind this, you can understand this result very easily. And then I will erase the board. So take some notes if you haven't, take the critical notes if you haven't done so. Okay, so a preliminary version of what I wrote on the board is available already on the Canvas website. This is what we're going to do moving forward. The notes on the Canvas doesn't contain everything that's worked out in details in class. So you are expected to do your own notes. So we talked about the basic transfer function analysis and block diagram relationship. Now let's move on to go to a little bit advanced, not too much, but slightly more advanced. So we have, let's do this one. Let's do plus. Suppose I have a section of the block diagram like this. First goes through a transfer function, and then there will be a summing junction and then a pass. So it turns out this block diagram is equivalent to, we can write it this way. Sometimes it's convenient to have the summing junction. We can move summing junctions in essence. We can move the summing junction to here and then analyze things often in a slightly more convenient way. So it's equivalent if let's say this is U and then this is U. If I want to have the summing junction to the front of G1, let's see what we need to do. I'm going to put down some more signal indicators. Let's say this is E, this is Y. From the original block diagram, we see what does E equal to? E equal to G1U plus Y. So whatever I do, in the end, I must still maintain this relationship. So this signal, after some, let's say this is still to be worked out. After this dashed box, this E should be exactly the same signal. So we have summing junction and this is plus. So let's look at it in two branches, right? So U goes through the top branch. Let's see how we can construct a G1 times U. What should this be in order for me to get a G1 times U? So U pass through here. So this should be G1. So in this way, I can get G1 times U. And then in the bottom over here, we need, let's say this is Y, okay? So what should this block be in order for whatever I add up in the end, I will still get a Y? I'll answer a question in a minute. All right? So that's 1 over G1. That's how you move a summing junction. I can move the summing junction to the front. And the way that I have to maintain the signal relationship is I move it to the front. On the top channel, I still have G1. But in the bottom channel, because I shifted the location over here, I have to do 1 minus G1, 1 over G1. So that's the block that I need to add. There's a question? Okay. So that's how you move a summing junction. Let's now look at something easier. We can move also pickoff points as well. So suppose I have this, I'm going to say G1, and then I have not a summing junction, but I pick up this signal. I branch it into a second channel. So let's call still, this is U, this is, let's say still E, and then we know this signal equals to U in this setup. Now I want to move the pickoff point. I want to move this one to the right-hand side. So I want to pick up from here. So this is still a question mark yet. And then get the output Y. So what should be the block such that I still get Y equal to U? So U pass through here become G1U, and then you pass through here. In order for Y to be equal to U, you should have 1 over G1. So that's how you move a pickoff point. Now with these, you can actually analyze many complex feedback systems. You know how to move summing junctions, you know how to move pickoff point. So you can see here, this pickoff, the summing junctions. Now we can actually soon be able to analyze this one. So let's work on a example. Look at this block diagram. Input, first there is a feedback, local feedback loop with a summing junction plus positive feedback. And then you branch out the signals. So the signal here goes through 2 additional summing junctions. It gets added to here, and then it also gets added to the outside. Take a moment to think about how you can move summing junctions or pickoff points to make things nicer to analyze. I'll give you 5 minutes. It's exactly the same logic. I want to simplify this local feedback loop. And then the way that I'm going to do is I'm going to move this pickoff point to here. Then this is standalone. So if I want to move to here, from here to here, what should be the construction? So this is equivalent to, I'm just going to write out this local section. So I want to have the pickoff to be here. It has to go through some block diagrams to make things to be equivalent. So let's say I'm going to put 2 blocks tentatively over here, and then there are remaining things. What should be these 2? I pick off from here. So that means originally my signal is, let's call this E. Originally this line is just E. Now this line becomes E. This is G1 times E. So in order for this to be E, this should be 1 over G1. And then originally over here, this signal, let's call it to be Y1. Originally, Y1 goes into the summing junction. Now, Y1 has to go through this block and then to this summing junction. So fortunately, we don't need to change. It's just the identity. Okay, so now this one is easier. We can simplify this one. So let's worry about it later now. So let's complete the remaining pictures. I have, this is E, this is still E. And then let's call this to be Y2 in the middle. I don't like this kind of pick off this way. It makes things a little bit not so easy. What I want to do is I see there are 2 channels. E goes into the first summing junction. E goes into the second summing junction. What I want to instead is to create this loop. So I don't want this additional branch to come out from here. I want it to be having 2 clean forward passes. So the same signal, so this is E. The same signal you can see goes through 2 summing junctions. So I go through 1 summing junction, 2 summing junction. That's what I want to do. So what should I put in here in order to make these 2 equivalent? So let's look at the signal again. This is Y1, and then this is E. This is still E, right? So we need to make sure whatever we do, this is still E. So you can see E pass through G1, and then pass through this channel, reach our second summing junction. To make this E and this E the same, this one should be 1 over G1 as well. So now this way I have 2 clean parallel passes, and the benefit is now I can simplify this one now. You can see this middle section over here, now we can write it very easily. All right, so let's finish up the last piece. So Y2 goes into G2 and then reach the summing junction. I have Y2 goes through, nothing actually changes here, and then go to the summing junction. Any questions? Okay, now we're actually almost there. for the first section, this is a feedback loop. We talked about the transfer function terminology. This one turns out to be g1 over 1 minus g1. This is positive feedback, okay? So remember, if this is negative feedback, it's 1 plus g1. If this is sign changes, you're going to become negative sign. So this is taken care of. For this one, this is 2 parallel passes. So this one is equivalent to 1 plus 1 over g1. So these 2 transfer function blocks added together. Okay, so now we have so forget about this and just think of this whole block to be this single transfer function. So what do we have now? I have 2 parallel passes again. One parallel pass, another parallel pass. So amazingly simple as well. So in the second parallel pass, I have this transfer function go through a second transfer function. So the overall, this one should be g2 1 plus 1 over g1. So this is the bottom block. Now, I have another parallel pass. So adding entirely here, one parallel pass is 1 over g1. So I just add the top branch. This is the overall transfer function for all of these. And then you can see this is so now I have first the block of transfer function, second block of transfer function. So overall, everything from the input side to the output side, overall is going to be, let me see if they can, I think still captured. So overall is going to be g2 1 over g1 plus, so it's just these 2 big chunk of transfer functions multiplied together. That's how, from initially seemingly cumbersome transfer function using these arithmetics of transfer function block diagram analysis, you can quickly get this. All right, I'll stop here. So as a homework, not homework, but second exercise, work on this one. Yes, this one? Oh yes, so this is a minus sign. I didn't read this carefully enough. It's minus, and then it's going to be good catch. There's another question somewhere? Okay, good. All right, that's so much for today. See you tomorrow.